In this lesson, we will cover antiderivatives. Let's start with a definition. For some function f that is defined on an interval, capital F is called an antiderivative of f if, when you take the derivative of capital F, it's equal to f. And that happens for every single x value on the interval from a to b. Let's make sense of this definition by using a very simple example. Here I have the function f of x is equal to x squared, and technically this should be defined on some interval. Any interval will do, but I'll say the entire real line, from negative infinity to positive infinity. That is where this function is always defined. Up to this point, we've talked about what it means to take the derivative of this function. So going from here to here by taking a derivative. We have rules for this, and the answer is 2x. And this is also defined on the entire real line. Now, an antiderivative is doing this process in reverse. So here, capital F of x is going to be the antiderivative of f. And what that means is we want to think of some function that's defined on the interval from negative to positive infinity. We want to think of some equation that when we take the derivative, the answer is going to be x squared. So we're working backwards with our derivative rules. Let's try to think about what that could be equal to. So capital F of x. Basically, we're going to have to use a guess and check approach. Well, it has to be x to some exponent. Oh, and when you take the derivative of something, the exponent will drop down by 1. Since this is squared, I know this should be 3. So here's my guess. So I'll note that this might not be the right answer, but at this point, this is just a guess. Is my guess correct? The way we could check is by taking the derivative of this equation, and if it equals this, then it's the right answer. So let's check the guess. If I take the derivative is 3x squared, and it was supposed to be x squared, and it's not. But that means we're pretty close. We have an x squared and x squared. The issue is this 3 should not be here. So we can go back and refine our guess. We can make a new guess. So I like the x cubed, but maybe I'll also divide it by 3. That way when I bring the 3 down front, it'll cancel with this 3, meaning I'll just have a 1 and then also an x squared. So again, this is also a guess. I think it's a better guess, but let's see if it's correct. If I take the derivative of this function, I get 3x squared over 3. The 3's cancel, and we in fact do get x squared. So what is capital F of x, the antiderivative? It's this. This was correct. And this is what it means to be an antiderivative of a given function. No matter how complicated it is, we're always looking for the same thing. Something that goes here so that when we take its derivative, it'll take us back to this thing here. Now, was this the only guess that would have worked? Are there others? It turns out there's infinitely many other choices that could have worked too. For example, if I let f of x equal x cubed over 3 plus 1, does this also work? And the answer is yes. And the reason is, when you take the derivative of this part, you'll bring down the 3. It'll cancel with the 3 in the denominator. We'll have x to the power of 2. But this constant of 1 is going to drop down to 0. It turns out for this function that when you take its derivative, you still get x squared. In fact, I could have put any number here. I could have put 7, -4, pi squared. As long as the thing that you put here is a constant, when you take the derivative, it will become 0, taking us back to the same answer. This brings us to the second part of this definition. The most general antiderivative of a function f is capital F of x plus c. This is the most general antiderivative. So from here, what that means is if we're asked to find the most general antiderivative, we'll go through this process of guessing what the answer is, and then we'll just put a plus c at the end, meaning any constant will do. In example 1, let's find the most general antiderivatives for all of these functions. So let's start with this one here. F of x is equal to 5x to the fourth. So here we're just trying to guess what capital F should be equal to. And, well, it's got to be x to the fifth, so I'll leave this as my guess. And this actually works out perfect. If we take the derivative of this function, we bring down the 5, copy down the x, subtract 1 from the exponent, and great, that worked. But if we're looking for the most general antiderivative, capital F of x is going to be x to the fifth plus c. The fact that this was a 5 and this was the 4 made the function pretty easy to come up with. Now down here, what if we change that 5 to a 6? So we'll switch it up a little bit here. What could we guess now for capital F of x? What would that be equal to? Well, we still have to have an x to the fifth. I think we'll have to leave this 6 in front of this function, and we could use this as our guess. But thinking ahead, this isn't going to work. If you bring down the 5 and multiply it to the 6, you get 30 x to the fourth, and I only wanted 6. What could I do to correct this? We can divide the whole thing by 5. I believe this will work because if you bring down the 5, it'll still cancel with this 5, this 6 will be left over, and we'll have x to the power of fourth. If I put a plus c at the end, this should be the most general antiderivative, but we can also check by taking the derivative. Okay, to differentiate this thing here, we bring down the 5. You could even write that as 5 times 6, which is 30, x to the fourth over 5. And then we take the derivative of the constant is 0. 5 goes into 30 6 times, and we do in fact get 6x to the fourth. Now, what if we have a sum of functions? So here we have 3 pieces. What could we guess for the antiderivative here, the most general antiderivative? Well, what we can do is look at each piece individually and try to figure out what the antiderivative is. So we'll start with x squared. Well, I know this has to go to x cubed, but if I take the derivative of this, it'll put a 3 in front, which I don't want. And the trick is you can, well, divide by 3. We can use the same logic on the next piece too and add it to our previous answer. Here we have x to the first, so I know it has to go to x squared. I know the answer can't be x squared because it'll put a 2 in front, which there is no 2 here, but the way around this is to divide it by 2. Then we have this plus 1, so again I could add something whose derivative goes back to 1, and that thing is going to be x itself. The derivative of x is just 1. If I put a plus c at the end, that is the entire answer, the most general antiderivative. Now, what about this one here, the square root of x? Just like with taking the derivative, it made sense to use the exponent of 1/2. Okay, well, from here, what would f of x be equal to? It's got to be x to a power, but what power would that be? I'm going to note that there's a pattern that's happening in all of these examples, and I'm going to put it over here. If you have x to a power, what did we do to figure out all of these pieces? We looked at this exponent and we said it had to be 1 bigger. Therefore, we added 1 to that exponent. So, like here, this was x squared, and I raised it up to a power of 3 by adding 1 to the 2. But we had this new number, and, well, when you bring it down, you'd like to cancel it. So you can just divide by that brand new number. As a rule, you can write it like this. In general, if you have x to a power of n, to get the antiderivative, you can add 1 to the exponent, and then divide by whatever that new number happens to be. I will note that the only time this rule doesn't work is if n is equal to -1, but that's just because you'd be dividing by 0 in the denominator. So I'll say, well, as long as this doesn't happen, I think this rule is always true. Let's try to use it here. This is a 1/2. What exponent should I put up here? It should be 1 more than 1/2. So essentially, I'll take 1/2 and I'll add 1 to it, which is the same thing as adding 2/2. I think the exponent we want is 3/2. This rule says we should divide by this new number, so I'll put divided by 3/2. If I put a plus c at the end, that should be the most general antiderivative. I don't like this dividing by with a fraction in the denominator. We can multiply by the reciprocal of this thing, will give us 2/3 in front. I'm going to write the function f of x as 2/3 x to the 3/2 plus c. Before moving on, let's actually make sure this worked by taking the derivative of this equation. So we're going to check our work for this last part here. F prime of x is equal to, okay, there's a 2/3 here, and you're going to bring the 3/2 down front. That is 2/3 times 3/2 times x. If you subtract 1 from 3/2, you get 1/2. And the derivative of c, a constant, is 0. Hey, what do you know? 2/3 times 3/2 is equal to 1, and that means f prime of x is just equal to x to the 1/2 power, which is the square root of x. The takeaway here is this rule will always work for us, provided that n is not equal to -1, and that is it for this example. Throughout the course of the semester, we've developed a ton of derivative rules. If you reverse them, you get rules for antiderivatives. Let's see if we can apply those here by finding antiderivatives for these particular functions. Let's start with cosine of x. Can we think of a function, capital F of x, whose derivative is cosine? Well, it's got to be sine, or at least has to relate to sine. Will sine of x work? This actually gets confusing here when you start using sines and cosines. The derivative of cosine is negative sine, but here we're looking for the antiderivative. So I do think we just want +1 sine of x. I'll put a plus c after it. I believe this is the answer. And that's because if you take the derivative of sine, you do in fact get cosine. Now, what about for the next one? F of x is equal to 2 sine of x. Again, if we're trying to guess the answer, it might be okay to say, well, okay, I can just copy down the 2, but maybe it's going to be cosine of x. Is this correct? Here, if you take the derivative, it's not going to work. You get 2, but the derivative of cosine is negative sine. So you get -2 sine of x, and then the constant goes to 0. So it didn't quite work. The way to fix this is to instead put a negative in front of it. So -2 cosine of x plus c. This is in fact the correct antiderivative. The reason it works is when you take the derivative of cosine, it'll introduce a negative, and this extra negative will cancel to make it +2 at the very end. So when going backwards from cosine, it goes back to positive sine, but when going backwards from sine, it goes to negative cosine. This becomes very confusing when using derivative rules and antiderivative rules together. What about this next one? 4 secant squared of x. So the goal here would be, all right, we just have to hopefully think of some function that we've encountered whose derivative is secant squared, and we'll multiply that thing by 4. And we do have a function for that. That's tangent of x. Here, if you take the derivative of this function, if you look at f prime of x, you get 4 times the derivative of tangent is secant squared, and then the constant goes to 0, so this does in fact work. We've also worked with exponential functions. What about this one? 2 to the x and e to the x. Can we figure out what capital F of x would be in this case? E to the x is great. Its derivative is also e to the x, and therefore its antiderivative is e to the x as well. But what about 2 to the x? Do you remember that? Do you remember what it means to take the derivative of not e to the x, but 2 to the x? The rule we came up with was Well, it's 2 to the x times the natural log of 2. But here we're going backwards. And the way around this is to not multiply by the natural log of 2, but divide by it. So when figuring out the antiderivative of 2 to the x, it's going to be 2 to the x divided by the natural log of 2. The reason is when you take the derivative of this thing, you'll multiply by a natural log of 2, and it will cancel with the 1 in the denominator. If we move on to the e to the x part, that is also e to the x, and we'll add on an arbitrary constant. And for this last one, f of x is equal to 5 over 1 plus x squared plus 5/3. What about this? It might be nice to rewrite this one just a little bit. Write it as 5 times 1 divided by 1 plus x squared plus 5/3. So I'm slightly changing the way this one is expressed. I'm just basically removing the 5 from the exponent. What do we do in this case? Can we think of some function whose derivative is 1 divided by 1 plus x squared? And we do have a function for that. That was arctangent or tangent inverse. Therefore, if we want the antiderivative, it is 5 times arctangent of x. And this is because arctangent goes to this very expression here. Now, what about this 5/3? What function would I put here so its derivative is 5/3? And that is 5/3 times x. If you have x and a number in front of it and you take the derivative, it just drops down to that number. That number can be a fraction, it can be a whole number, but this will always work. I'll put a plus c at the very end, and this is the answer. In example 2, let's continue with finding the most general antiderivatives, but just for a couple of more complicated functions. Starting with this one, f of x, we have 4 separate parts to it. I know how to find the antiderivative of the first and second parts. What about these two fractions at the end? Here I have 5x cubed over x, and here I have x over the square root of x. For this fraction, for example, can I find the antiderivative of the top and divide it by the antiderivative of the bottom separately? And the answer to that is no. But what you can do is simplify this fraction and simplify this fraction. By that I mean, if you have 5x cubed over x, you could simplify this to 5x squared. You can change this into something that we have rules for. The same thing goes for x divided by the square root of x. So if you have this divided by this. This is the same thing as x divided by x to the 1/2. If you subtract the exponents, 1 minus 1/2 is simply a half. So this is equivalent to this. I'm going to rewrite this function and replace this piece and this piece with these two things. That is, f of x is really equal to 4 cosine of x minus 2 sine x plus 5x squared minus x to the 1/2. Written this way, I now have rules for each individual part. We can now go through and find the antiderivative capital F of x. Starting with 4 cosine of x, it's going to be 4. Okay, with sine and cosine, it's either sine or negative sine. Which is it? It's sine. And the reason is the derivative of sine is cosine. Next, we have minus 2. Okay, sine goes to either cosine or negative cosine. Maybe it's just negative cosine. And the answer is, well, that's not going to work. When you take the derivative of cosine, it goes to negative sine. The extra negative will make this positive. Therefore, I have to make this positive. When you take the derivative of cosine, you get negative 2 sine. Next, we have 5x squared. Okay, that'll be 5x cubed over 3. Then minus, okay, when we have x to the 1/2 power, we will add 1 to the exponent, and divide by that new number. I'll then put a plus c at the end. This isn't completely simplified, but this is the most general antiderivative of the function lowercase f. I think really the only thing to simplify would be maybe put a 2/3 in front of the x to the 3/2, but other than that, this looks great. Now, what about the antiderivative of g of x, which is a product of two functions? Can we simply just find an antiderivative for the first and the second piece separately and multiply them together? And again, the answer is no, we can't do that. We can rewrite this function in a way where we can find this antiderivative. And the trick here is to actually multiply this thing out. That is, take the x and multiply it into the parentheses and do the same thing with the 2. This function becomes 2x squared plus x plus 4x plus 2. And when you combine like terms, that's 2x squared plus 5x plus 2. I'm not going to find the antiderivative by looking here. I'll look here instead. So to find, I'll call it capital G of x. The antiderivative of 2x squared is 2x cubed over 3. The antiderivative of 5x is 5x squared over 2. The antiderivative of 2 is just 2x. And I'll put a plus c at the end. So why can't we simply just, when you see a fraction, take the antiderivative of the top and bottom separately? And also, why, when you look at a product, why can't you just find the antiderivative of the two pieces separately? The reason is, when it came to products and quotients, we had specific rules for dealing with the derivatives of those things. For the product rule, it was u prime v plus uv prime. That means the antiderivative of this whole thing is equal to just u and v. And that is not what I see here. So we can't just look at each piece individually. And likewise, with a quotient, when we had u divided by v, again, it was a much more complicated formula. It was the bottom times the derivative of the top, minus the top times the derivative of the bottom, all over the bottom squared. You have to see this in order to go backwards to this fraction. So for this reason, if we see fractions or products, at this point we should think, well, maybe we can somehow simplify this to something we can find the antiderivative of. And the same thing goes for a product. Hey, maybe we can multiply these things together to get to our final answer. In example 3, I'd like to find the antiderivative capital F of f, the function given here, that satisfies the condition f of 0 is equal to 5. Up to this point, we've always found the most general antiderivative, meaning we'd come up with a function f of x, and we would add an arbitrary constant c at the end. If we're given a condition like this, it means we're going to actually have to find a specific number c for which this statement will be true. So this will be our most general antiderivative, but we can use this to figure out the value of c for which this will be true. This process will start by still finding the most general antiderivative, so let's do that. Capital F of x is equal to, okay, for 4x cubed, that's going to be 4x to the 4th over 4, minus, then we have 6x cubed over 3, plus x plus c. So here I just added 1 to the exponents and divided by the new number, and I see here that things will cancel, and so we get that f of x, capital F of x, is equal to x to the 4th minus 2x cubed plus x plus c. Now, if you put 0 into this function, you get the arbitrary constant c back, but that's not what we want. We actually want the value at the end to be equal to 5. Here's what that would look like. If you put 5 here and 0 in place of all the x's, it should be that c is equal to the number 5. Just to check that, this statement means 5 is equal to 0 to the 4th minus 2 times 0 cubed plus 0 plus c. On the left, we get 5. On the right, that simplifies to c. And therefore, the answer we're looking for is capital F of x is equal to x to the fourth minus 2x cubed plus x plus 5. This is no longer the most general antiderivative. We found a specific antiderivative, and that just means you're finding the correct constant c. Now, what if we switch this up a little bit and say, well, I don't want this condition to be true, but I want this condition instead. Capital F of 1 is equal to negative 2. What does that mean in this case? It means that we're going to find a different number for c. So basically, I'll go back to the most general antiderivative, I'll put in this information, and I'll find a number c, and it will probably be different than the one that we found here. So let's try that. So here, if f of 1 is equal to negative 2, I'll go to this antiderivative, I'll put negative 2 here, and a 1 in place of the x's. It will allow me to solve for c. That means we get negative 2 is equal to 1 to the fourth minus 2 times 1 cubed plus 1 plus c. If we simplify this, okay, negative 2 is equal to 1 minus 2 plus 1 plus c. So negative 2 is equal to, we get 2 minus 2, which is 0, and that gives us c is equal to negative 2. Okay, the answer for this one is, the antiderivative is capital F of x is x to the fourth minus 2x cubed plus x minus 2. It's nice to have a most general antiderivative because the second you have that, you can start saying, well, what if we put conditions on the antiderivative? That amounts to finding the value of c that will match up with the given condition. Before we try example 4, I'd like to recall this derivative rule. The derivative of the natural log of the absolute value of x is equal to 1 over x. Now, this rule is true because if you think of the absolute value of x, it's either plus or minus x, depending on whether x is positive or negative. If it's positive x, this rule is saying, what's the derivative of the natural log of just x? And we know that. It's 1 over x. But what if you take the derivative of the natural log of negative x? What's that? Well, it's 1 over negative x. But by the chain rule, you have to multiply by negative 1. The negative in the numerator and the denominator cancel to again give you 1 over x. So whether you use positive or negative x, you always go back to the same thing, which is 1 over x. We will use this idea in example 4. I'd like to find the antiderivative, capital F, of f of x is equal to 1 over x, such that capital F of negative 1 is equal to 7. And here I included a graph of 1 over x. So to start this problem, you have f of x is equal to 1 over x, no problem. And if you're not being careful, you might think, oh, well, I know the function that this comes from. That function is the natural log of actually just x, and we'll add on a constant c as the arbitrary constant. We can now look to this information here. I'll put 7 in place of f of x, and I'll put negative 1 in place of this x. So plugging this information into this equation, we get the following. 7 is equal to the natural log of negative 1 plus c. And then we'd go ahead and solve for c in this equation here. But if you take the natural log of negative 1, you get an error message in your calculator. You can't take the natural log of a negative number. So it's like this process stops. But if you look at the graph, I mean, this should be possible. Here at negative 1, the actual graph of 1 over x exists, and therefore there should be some antiderivative. And that's where this rule comes into play. If you have 1 over x as your function, the antiderivative is not simply the natural log of 1 over x. It's actually the natural log of the absolute value of x. It is vital to, when finding the antiderivative of this function, to put an absolute value around the x, like this over here. So the takeaway is, this is close to being correct, but without the absolute value, it's not correct. The function I will be using for this is capital F of x is the natural log of the absolute value of x plus c. Written this way, we're now allowed to actually use this information in this equation. I'll put 7 in place of f of x, and I'll put -1 in place of this x. We get the following. 7 is equal to the natural log of the absolute value of -1 plus c. And we can take the absolute value of -1, that's just +1, and the natural log of 1 is 0. And that means c is equal to 7. So the final answer to this problem is the function we want, the antiderivative, is the natural log of the absolute value of x plus 7, and that is it for this problem. In example 5, let's find the antiderivative capital F of f of x is equal to 5x to the fourth minus 3x to the fifth, such that this condition is met on the antiderivative. Here I've actually included a graph of lowercase f here in blue. So let me just mark that this is f of x. I'm going to start by finding the most general antiderivative of lowercase f. So that is going to be 5x to the fifth over 5 minus 3x to the sixth over 6 plus an arbitrary constant c. And we can simplify this as capital F of x is equal to, well, that's really just x to the fifth minus x to the sixth over 2 plus c. I'm given that f of 0 is equal to 1. I'll put 1 here and 0 here, and that actually tells me what c is equal to. C is equal to 1. So 1 is equal to 0 to the fifth minus 0 to the sixth over 2 plus c, and therefore c is equal to 1. I've found the antiderivative that I'm looking for. It's x to the fifth minus x to the sixth over 2 plus 1. I'm going to plug this function into my graphing calculator and sketch what I see over here and just try to make a connection between what's happening on the graph of f and its antiderivative. So here are the connections that I'm trying to make. This is the derivative of this. Any place where this is positive means this function must be increasing. So here the derivative is positive, 0, and positive right up until this point here. I'm expecting this function to be increasing from here until we get to this spot here. Now the derivative is negative, and that means I'm expecting this graph to be decreasing. So whatever this looks like, I'm expecting, it's increasing, and then here's going to decrease. Furthermore, since this is the derivative of this, the derivative is 0 here and here. And that means the graph, this thing will be horizontal at this point and this point. I'm going to now sketch this and see what we get. It goes to the point 0, 1. The function is increasing, which I was anticipating, and then it actually levels off here just for a moment because the derivative is 0. And then it continues to increase thereafter until about here. I see something that it's increasing, and then right about here, it turns around and starts dropping down and is decreasing. This highest point corresponds to where its derivative is equal to 0. The derivative is negative, and therefore the graph starts decreasing. My sketch isn't perfect, but all the things that we know about derivatives hold true here. Here the derivative is positive and positive and positive and positive, and the antiderivative is increasing. Here the derivative is negative, and the antiderivative is decreasing. Here the derivative is 0, the antiderivative is horizontal. Here the derivative is 0, and again the antiderivative is horizontal. So you can still infer what this graph will look like because this is the derivative of this. In example 6, we're told a particle moves along a line with acceleration a of t is equal to 2t plus 3. And we're also told that it has an initial displacement of 6 centimeters and an initial velocity of -3 centimeters. Can we use this information to find the position of the particle s of t? So just as a reminder, if you know the position of a particle and you take its derivative, this told you the velocity. And if you take the derivative of the velocity, or you take the second derivative of the position function, this thing told you the acceleration. So if you know this thing, you take the derivative, you get velocity. And if you know this thing, you take the derivative again, you get acceleration. We define antiderivatives to go backwards from taking a derivative. What this means is, if you know your acceleration, you can go backwards by using antiderivatives to figure out not just the velocity, but the original position as well. Let's try that process out. Here's the acceleration. It is 2t plus 3. What is the velocity function equal to? Well, the derivative of velocity goes to acceleration, so the antiderivative of acceleration will go to velocity. Basically, we just have to find the antiderivative of this function. Well, the antiderivative of 2t is t squared. The antiderivative of 3 is 3t. We have to add on an arbitrary constant c to find the most general antiderivative. Ideally, I'd like to know what this number c is equal to. How can we figure out what this c equals? Well, we're told the initial velocity at 0 is equal to -3. What we can do is put -3 here. We can put 0 in place of t, and that will allow us to solve for c. So -3 is equal to 0 squared plus 3 times 0 plus c. And when you simplify this, you get that c is equal to -3. We now have our velocity function. It's equal to t squared plus 3t minus 3. The ultimate goal is to find the position of the particle s of t, but if we're looking for that, if we want to know what s of t is equal to, since the derivative of s of t goes to v of t, the antiderivative of v of t goes to s of t, meaning I need to find the antiderivative of this. Well, that's going to be equal to t cubed over 3 plus 3t squared over 2 minus 3t plus, I'll use a different letter since we already used c. Logical choice B, let's use the letter D. To complete this problem, I need to figure out what D is equal to. And we're told the initial displacement is 6. So I can use this piece of information to figure out what this is equal to. What I'll do is I'll put 6 in place of s of t and 0 in place of all of these t's, leaving d left over. When we do that, we have 6 is equal to 0 cubed over 3 plus 3 times 0 squared over 2 minus 3 times 0 plus d. This all reduces to 6 is equal to d. What is the final function s of t equal to? It's t cubed over 3 plus 3t squared over 2 minus 3t plus 6. And this is the final answer.